Hi everyone, welcome back to this video on cryptocurrency, public child key derivation. As mentioned previously, a very useful characteristic of HD wallets is the ability to derive public child keys from public parent keys without having the private keys. This gives us two ways to derive a child public key, either from the child public key or directly from the parent public key. An extended public key can be used therefore to derive all of the public keys and only the public keys in that branch of the HD wallet structure. This shortcut can be used to create very secure public key only deployments where a server or application has a copy of an extended public key and no private keys whatsoever. That kind of deployment can produce an infinite number of public keys and Bitcoin addresses, but cannot spend any of the money sent to those addresses. Meanwhile, on another more secure server, an extended private key can derive all of the corresponding private keys to sign transactions and spend the money. One common application of this solution is to install an extended public key or a web server that serves e-commerce application. The web server can use the public key derivation function to create a new Bitcoin address for every transaction, e.g. for a customer shopping cart. The web server will not have any private keys that will be vulnerable to theft. Without HD wallets, the only way to do this is to generate thousands of Bitcoin addresses on a separate secure server and then preload them on the e-commerce server. That approach is cumbersome and requires constant maintenance to ensure that the e-commerce server doesn't run out of keys. Another common application of this solution is for cold storage or hardware wallets. In that scenario, an extended private key can be stored on a paper wallet or hardware device such as a Trezor hardware wallet, while the extended public key can be kept online. The user can receive addresses at will, while the private keys are safely stored offline. To spend the funds, the user can use the extended private key on an offline signing Bitcoin client or sign transactions on the hardware wallet device. E3 Trezor figure 511 illustrates the mechanism for extending a parent public key to derive child public keys. So you can see parent key public 256 bits, parent chain code 256 bits, index number 32 bits, e.g. 0HMAC SHA512, 512 bits, output one-way hash function, child public keys 264 bits, child index 0, chain code 256 bits. Using an extended public key on a web store. Let's see how HD wallets are used by continuing to store. Let's see how HD wallets are used by continuing our story with Gabriels web store. Gabriel first set up his web store as a hobby based on a simple hosted WordPress page. His store was quite basic with only a few pages and an order form with a single Bitcoin address. Gabriel used the first Bitcoin address generated by his Trezor device as the main Bitcoin address for his store. This way, all incoming payments will be paid to an address controlled by his Trezor hardware wallet. Customers would submit an order using the form and send payment to Gabriel's published Bitcoin address, triggering an email with order details for Gabriel to process. With just a few orders each week, this system worked well enough. However, The little web store became quite successful and attracted many orders from the local community. Soon Gabriel was overwhelmed with all the orders paying the same address. It became difficult to correctly match orders and transactions, especially when multiple orders of the same amount came in close together. Gabriel's HD wallet offers a much better solution through the ability to derive public child keys without knowing the private keys. Gabriel can load an extended public key XPUB on his website, which can be used to derive a unique address for every customer order. Gabriel can spend the funds from his Trezor, but the XPUB loaded on the website can only generate addresses and receive funds. This feature of HD wallets is a great security feature. Gabriel's website does not contain any private keys and therefore does not need high levels of security. To export XPUB, Gabriel uses the web-based software in conjunction with the Trezor hardware wallet. The Trezor device must be plugged in for the public keys to be exported. Note that hardware wallets will never export private keys, those always remain on the device. Figure 512 shows the web interface Gabriel uses to export the XPUB. Gabriel copies the XPUB to his web store's Bitcoin shop software. He uses Mycelium Gear, which is an open source web store plugin for a variety of web hosting and content platforms. Mycelium Gear uses the XPUB to generate a unique address for every purchase. Hardened child key derivation. The ability to derive a branch of public keys from an XPUB is very useful, but it comes with a potential risk. Access to an XPUB does not give access to child private keys. However, because the XPUB contains the chain code, if a private key is known or somehow leaked, it can be used with the chain code to derive all the other child private keys. A single leaked child private key together with the parent chain code reveals all the private keys of all the children. Worse, the child private key together with the parent chain code can be used to deduce the parent private key. To counter this risk, HD wallets use an alternative derivation function called Hardened derivation, which breaks the relationship between parent public key and the child chain code. The Hardened derivation function uses the parent private key to derive the child chain code instead of the public key. This creates a firewall in the parent-child sequence with a chain code that cannot be used to compromise a parent or sibling private key. The hardened derivation function looks almost identical to the normal child private key derivation, except that the parent private key is used as input to the hash function instead of the parent public key as shown in the diagram 513. When the hardened private derivation function is used, the resulting child private key and chain code are completely different from what would result from the normal derivation function. The resulting branch of keys can be used to produce extended public keys that are not vulnerable because the chain code they contain cannot be exploited to reveal any private keys. Hardened derivation is therefore used to create a gap in the tree above the level where extended public keys are used. In simple terms, if you want to use the convenience of an XPUB to derive branches of public keys without exposing yourself to the risk of a leaked chain code, you should derive it from a hardened parent rather than a normal parent. As a best practice, the level 1 children of the master keys are always derived through the hardened derivation to prevent compromise of the master keys. Index numbers for normal and hardened derivation. The index number used in the derivation function is a 32-bit integer. To easily distinguish between keys derived through the normal derivation function versus keys derived through hardened derivation, this index number is split into two ranges. Index numbers between 0, 2, 3, 1, minus 1, 0x 0, 2, 0x 7, f, 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 f are used only for normal derivation. Index numbers between 2, 3, 1 and 2, 3, 2, minus 1, 0, x 8, 0, 0, 0, 0, 0, 0, 0 to 0x f, 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 f are used only for hardened derivation. Therefore, if the index number is less than 231, the child is normal, whereas if the index number is equal or above 231, the child is hardened. To make the index number easier to read and display, the index number for hardened children is displayed starting from 0 but with a prime symbol. The first normal child key is therefore displayed as 0, whereas the first hardened child index 0x8, 0, 0, 0, 0, 0, 0, 0 is displayed as 0. In sequence then, the second hardened key would have an index of 0x8, 0, 0, 0, 0, 0, 0, 1 and will be displayed as 1 and so on. When you see a HD wallet index I, that means 231 plus I. HD wallet key identifier path. Keys in a HD wallet are identified using a path naming convention, with each level of the tree separated by a / character. Table 5.6 private keys derived from the master private key start with M. Public keys derived from the master public key start with M, therefore the second child private key of the master key is M/0. The first child public key is M/0. The second grandchild of the first child is M/0/1 and so on. The ancestry of a key is used to read from right to left until you reach the master key from which it was derived. For example, identifier MXYZ describes the key that is child of key MXY, which is the yth child of key MX, which is the xth child of M. Navigating the HD wallet tree structure. The HD wallet tree structure offers tremendous flexibility. Each parent extended key can have 4 billion children, 2 billion normal children and 2 billion hardened children. Each of those children can have another 4 billion children and so on. The tree can be as deep as you want with an infinite number of generations. With all that flexibility, however, it becomes quite difficult to navigate this infinite tree. It is especially difficult to transfer HD wallets between implementations because the possibilities for internal organization into branches and sub-branches are endless. Two BIPs offer a solution to this complexity by creating some proposed standards for the structure of HD wallet trees. BIP 43 proposes the use of the first hardened child index as a special identifier that signifies the purpose of the tree structure. Based on BIP 43, an HD wallet should use only one level 1 branch of the tree, with the index number identifying the structure and namespace of the rest of the tree by defining its purpose. For example, an HD wallet using only branch MI is intended to signify a specific purpose, and that purpose is identified by index number I. Extending that specification, BIP 44 proposes a multi-account structure, a purpose number 44 under BIP 43. All HD wallets following the BIP 44 structure are identified by the fact that they only used one branch of the tree M44. BIP 44 specifies the structure as consisting of 5 predefined tree levels: M, purpose, coin, type, account, change, address, in. The first level purpose is always set to 44. The second level, coin type, specifies the type of cryptocurrency coin, allowing for multi-currency HD wallets where each currency has its own subtree. Under the second level, there are 3 currencies defined for now. Bitcoin is M44, Bitcoin testnet is M44-1, and Litecoin is M442. The third level of the tree is account, which allows users to subdivide their wallets into separate logical sub-accounts for accounting and organizational purpose. For example, an HD wallet might contain 2 Bitcoin accounts, M4400 and M4401. Each account is the root of its own subtree. On the fourth level, Change HD wallet has 2 subtrees, one for creating receiving addresses and one for creating change addresses. Note that whereas the previous levels used hardened derivation, this level uses normal derivation. This is to allow this level of tree to export extended public keys for use in a non-secured environment. Usable addresses are derived by the HD wallet as children of the 4th level, making the 5th level of the tree the address index. For example, the third receiving address for Bitcoin payments is the primary account would be M44002. Table 57 shows a few more examples. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing, subscribing and give me a thumbs up. Thank you.